you. So our next speaker is Dr. Agnes Lamacz-Keymling. She is a member of the Faculty of Mathematics from the University of Duisburg, Essen. She obtained her PhD in TU Dortmund under the supervision of Professor Ben Schweitzer. Her research interests include multi-scale and homogenization problems, in particular wave phenomena. For this afternoon or for this morning, she will talk on high-order homogenization in optimal control by the Bloch wave method.
Thank you. Thank you very much for the kind introduction. It's a pleasure to be here. So in this talk, which is based on a joint work with Irvin Yusept, I will present a corrector result for an optimal control problem with highly oscillatory periodic coefficients. We will see that the standard two-scale approach is not really appropriate in this case, which is why we have to apply a different, more suitable method, namely the so-called Bloch waves, which in the context of homogenization have mainly been developed in the 90s. So to really understand the challenges raised by optimal control problems, let me first of all recall standard results in classical periodic homogenization. In the simplest setting, one is interested in solutions U epsilon to this elliptic PDE here with right-hand side F. And as usually, the coefficient A epsilon in this equation is assumed to be highly oscillatory. That is of the form AY of X over epsilon, where this AY is a one-periodic, uniformly elliptic and symmetric coefficient function. So to avoid boundary layer terms, we consider this equation in the whole space Rn. And we also add this term U epsilon here to exclude regularity issues. So it is really the most fundamental model one can think of. However, the fast oscillations in the coefficient make this very simple equation already hard to treat, especially from the numerical point of view. And as you will all know very well, the main aim of homogenization is to derive a simpler, so-called effective model, which provides a good approximation of this original one, if the periodicity length epsilon is small. Actually, as the solution sequence U epsilon is uniformly bounded in H1, I mean, this is trivial, it follows directly from the equation, one can find the limit function U such that, at least up to a subsequence, U epsilon converges weakly to U as epsilon goes to 0. And the main achievement of homogenization is a characterization of this limit function U as a solution to this effective equation here with a constant effective coefficient matrix A star. So the limit function U is a non-oscillatory solution to a constant coefficient equation. And you will also know very well that this effective matrix can be calculated from AY through this formula, involving also an auxiliary function chi1, the so-called corrector of first order, which in turn can implicitly be calculated as periodic solution to this so-called cell problem. So all this is very standard up to now. Now, the next question one could ask is, what about the approximation quality of this limit function U? Does U epsilon converge maybe strongly in H1? Are there maybe convergence rates in, let's say, in L2? And actually, as U epsilon is a solution to a highly oscillatory equation, these high oscillations, of course, carry over to the solution itself, producing the following picture. So this is a typical behavior of U epsilon. And what you can see here is some non-oscillatory profile with many small fast oscillations around it. And these fast oscillations are typically of order epsilon. They're epsilon periodic. And so it is not very surprising that strong convergence in H1 or convergence rates in L2 better than epsilon to the alpha with alpha below 1 cannot be expected, because the oscillations already started order epsilon. And so in order to achieve better estimates, one needs to add an order epsilon correction with this highly oscillatory corrector chi1 times the gradient of U. So in some sense, this adapts the profile U to the microstructure. And since in our case, boundary layer terms were excluded, one can prove under appropriate assumptions that the approximation error is indeed of order epsilon squared in L2. Now, in the next step, one could try to obtain even better estimates by adding another highly oscillatory term of the form epsilon squared times the second corrector times the second derivative of u. However, at this point, one gets stuck. So it's not possible to obtain an order epsilon cube estimate here by just adding this term in general. Why? The problem is that it's not sufficient to just adapt the profile U more and more to the microstructure by adding more and more highly oscillatory terms. Instead, also the profile function U itself requires a higher order non-oscillatory correction. And to make this clearer, let me recall a well-known result, which, for instance, can be found in the book of Bakalov and Panashenko, and which relies on the very standard two-scale expansion. So in this classical approach, one makes a particular ansatz that U epsilon can be expanded in a series involving certain functions UN, which are assumed to be periodic in the second variable. In particular, this X over epsilon dependence here makes these functions highly oscillatory. And it's well known that this ansatz yields a hierarchy of equations characterizing these functions UN here. In particular, it is also well known that the first function U0 is independent of Y, and that it's simply the homogenized solution U. However, for the higher order functions UN, this hierarchy can be somehow very confusing and very hard to read. And so a very elegant way to arrange this result is the following. For each profile, UK in this expansion, we define a non-oscillatory profile UK tilde by simply averaging UK over this fast variable Y. And then it turns out that each non-oscillatory profile UK tilde is related to the preceding profiles through an effective equation involving constant effective coefficients B star. Okay, now next, by collecting all those non-oscillatory profiles into a single function, let's call it capital U epsilon, it turns out that the original two-scale ansatz is in fact equivalent to a power series where this profile U epsilon is adapted to the microstructure through infinitely many highly oscillatory corrector terms. And this is somehow the picture you should keep in mind for the rest of the talk. The behavior of U epsilon, the original solution, is somehow twofold. On the one hand, we have a non-oscillatory profile with contributions at several orders of epsilon. And on the other hand, this non-oscillatory profile is adapted to the microstructure through infinitely many highly oscillatory corrector terms. And in view of this, it's not very surprising that by truncating both series here, so the one for capital U epsilon and the one for the adaption, at order, let's say, capital N, one can achieve, under appropriate assumptions, an L2 error estimate of order epsilon to the n plus 1. And I mean, this also makes clear why we got stuck on the previous slide, because the correction of the non-oscillatory profile here starts already at order epsilon squared in general. And this is why we couldn't go beyond epsilon squared on the previous slide. Okay, so this is somehow the standard classical picture. And now let us make things a bit more complicated by considering an optimal control problem. In an optimal control problem, the goal is to minimize the cost functional J epsilon, say nicely convex and continuous, which depends on two functions, theta epsilon, the so-called control, and U epsilon, the state function. These two functions are related through a PDE constraint, which is exactly our elliptic highly oscillatory equation. So theta epsilon, the control, is the right-hand side, and U epsilon is the solution. Moreover, the control theta epsilon is restricted to an admissible set, also, let's say, convex and closed. Under this very standard assumptions, it is well known that this optimal control problem is well posed. So there exists a unique solution, an optimal control theta epsilon star and corresponding state U epsilon star. And also a homogenization result is available. Namely, it can be shown that theta epsilon star and U epsilon star are both uniformly bounded, such that limits theta star and U star exist, for which one can prove that there are in fact solutions to an effective optimal control problem. So this is very well known. Now, what about higher order estimates? So is it possible to derive a corrector result where the approximation quality in L2 is actually of order epsilon to the 2m, with m as large as one likes? For a reason which will become obvious a bit later on, these even powers of epsilon are important for us. We will stick to even powers here. But m can be as large as one likes. And the question is, can we find approximations such that the L2 error is actually of order epsilon to the 2m? Okay, now in the standard approach, the two-scale approach, one would simply expand theta epsilon star and u epsilon star in a two-scale series, and then truncate the series at order, let's say, 2m minus 1. However, this turns out to be a bad idea, namely due to the restriction of theta epsilon to an admissible set. Let me illustrate this with a small example. So, for instance, let's take u at to be the set of all controls such that the corresponding solution u epsilon is bounded in a 2 by a fixed constant L. Then, of course, one could expand u epsilon in a two-scale series truncate at order 2m minus 1. And then the trouble really starts because there is absolutely no reason why the truncation should satisfy this L2 condition. So in other words, truncating the series destroys our admissible set. We run off the admissible set. This is really a serious problem. So in what follows, we will therefore apply a different, more suitable method, which are the Bloch waves. Okay, so I suppose that most of you are not really familiar with Bloch waves. So let me start with a short general overview. Imagine that you have an L2 function u on Rn. Then, of course, this function u can be written as an integral of its Fourier transform u hat. Next, decompose the integration variable xi into an integer part k and some remainder eta, which then lies in the so-called reciprocal cell z, being minus 1/2 to the m. Okay, this is the result, the decomposed integral. We have a sum over k and an integral over z. Next, observe that this function here, denoted by capital F, is actually one periodic because only the integer k contributions appear. So it's one periodic. Now, of course, the one periodic function can be written as a sum over Fourier basis functions. This already happened here. But it can also be expanded by using a different set of periodic basis functions, which are more appropriate for our homogenization problem. And in our case, the natural choice would be to consider the one periodic eigenfunctions of the following operator. So it involves our heterogeneous periodic coefficient AY. And indeed, for each eta, this operator is nicely positive definite, it's self-adjoint. So for every eta, one finds a sequence indexed by m of non-negative eigenvalues, lambda m, and corresponding one periodic eigenfunctions phi m, which can be used to expand this capital F with certain prefactors, which are this here. Okay, next, by introducing omega m as phi m times this exponential factor here, and by the way, this omega m's are called Bloch waves, and plugging in the expansion of capital F into this formula, we end up with the so-called Bloch expansion of u. Okay, so basically the Bloch expansion of a function u consists of a sum over m, integral over z, including this Bloch functions omega m. Now, why are we doing this? What is the advantage? Well, the advantage is that, that our heterogeneous operator here simply acts as a multiplier on the Bloch expansion. Indeed, the basis functions omega m are simply the eigenfunctions for this operator. And so applying L to the Bloch expansion gives us exactly the same expansion, but with an additional factor lambda m, which is the eigenvalue. So this is the main idea of Bloch waves. Now, in order to apply this to our situation, we have to deal with a small technicality, because in our homogenization problem, we have ay of x over epsilon. So there is this scaling with epsilon. And for this reason, we have to introduce a rescaled version of the Bloch expansion by defining rescaled Bloch eigenfunctions or Bloch waves and rescaled Bloch eigenvalues. So this exact formulas are not so important to remember. What is really important is that the scaling is chosen in such a way that this rescaled Bloch functions are the eigenfunctions with eigenvalues lambda m epsilon, but this time for the strongly heterogeneous elliptic operator with the matrix A epsilon. Okay, and then also the Bloch expansion has a rescaled form. Now there is a sum over m as before and an integral over z over epsilon. And this expansion is constructed in such a way that our heterogeneous operator acts as a multiplier on this expansion. Okay, so this is the main idea. Now remember what we have learned from the classical two-scale approach. So there we had this non-oscillatory profile with contributions at several orders of epsilon on the one hand, and this non-oscillatory profile was then adapted to the microstructure through infinitely many highly oscillatory correctors. And actually, it turns out that there is an analog for this adaption process in the Bloch world. The so-called Bloch adaption, which was introduced by Konka, O'Keefe, and Vaninathan in 2002, is defined as follows. For a given function u in L2, we take its Fourier transform u hat, and we define the adaption by treating this u hat as a Bloch coefficient, the lowest order Bloch coefficient for the adapted function. So in other words, the adaption is defined as a Bloch series, including only the lowest order Bloch mode m equals 0. So the sum is gone, only m equals 0 appears. And the Bloch coefficients are simply the Fourier coefficients of u. Now, by construction, this adapted function is highly oscillatory. And indeed, for sufficiently smooth u, one can expand this adaption in powers of epsilon, obtaining something which is very, very similar to the classical adaption through highly oscillatory correctors. Okay, however, the Bloch adaption has a major property, namely, it turns out that for functions with at least compact support k in Fourier space, the Bloch adaptation preserves the L2 norm. Yeah, indeed, by Parseval's identity, the L2 norm of a adapted function is simply the L2 norm of the Bloch coefficients, which are u hat. This in turn are the Fourier coefficients of u, and this gives us the L2 norm of u itself. And this is a feature which will be used for the rest of this talk. Okay, now with this knowledge, we are now in the position to entirely formulate our optimal control problem. So our goal is to minimize the cost functional j epsilon, where the control theta epsilon is restricted to an admissible set u epsilon at, which will be discussed on the next slide. And u epsilon is related to theta epsilon through our PDE constraint. Now, concerning the cost functional, so we assume that it consists of three parts. There is an L2 norm of the control, theta epsilon. There is an L2 difference between u epsilon and some reference function u epsilon d2. And there is also an energy norm applied to u epsilon minus another reference function u epsilon d1. Now, what is this energy norm? Well, this is simply the energy corresponding to this PDE constraint, nothing else. Okay, now for the reference data, we also have to assume something, namely, we have to assume that both reference data are in fact adaptions of fixed functions ud1 and ud2. And we also have to assume that ud1 and ud2 have compact support k in Fourier space. Let me comment on this third assumption. So actually, as u epsilon is a solution to a highly oscillatory equation, it's highly oscillatory itself. And so in this sense, it is very natural to assume such highly oscillatory behavior also for the reference data. And I mean by saying that both reference data are in fact adaptions, we do exactly this. We assume that both reference data are highly oscillatory and adapted to the microstructure. And let me also mention that well-prepared data are in fact at the basis of many high-order corrector results in homogenization. So it is something which is quite common. It's a very natural assumption. Okay, now what about the admissible set? Well, also here we have to assume some kind of well-preparedness. And more precisely, we demand that U epsilon at is convex and closed, this is standard, and that there exists a fixed function theta 0 such that the adaption of theta 0 is always admissible. Now, so at the end, this assumption will guarantee that the sequence of optimal controls to our original problem is uniformly bounded. Now, the third and most interesting assumption is the following. We demand that for a given control theta, the projection of theta onto the lowest Bloch mode m equals 0 and eta in k. So we define the projection as by reducing this to m equals 0 and eta in k. And we demand that this projection in Bloch space is again admissible. Okay, later on, we will see how this assumption really comes in. What is for the moment important is the question, are these assumptions really realistic? And therefore, let me present a few examples. So as a first example, let's take U epsilon at to be the set of all controls theta, such that the L2 norm of theta is bounded by a fixed constant L. Then, of course, this set is convex and closed, and since the adaption of 0 is still 0, also the second assumption is satisfied. Now, concerning the third assumption, now, by simply using the Parseval's identity, we see that the L2 norm of the projection is exactly the L2 norm of the corresponding Bloch coefficients, which can be estimated by the sum over all Bloch coefficients, which in turn, due to Parseval's identity again, are again the L2 norm of theta itself, which is bounded by L by assumption. So the third assumption is indeed satisfied easily. However, there are also other situations we can deal with. So one example is the set of all controls such that the corresponding solution U epsilon is bounded in L2. This is exactly the example I showed you at the beginning of the talk. And also bounds on the energy of U epsilon can be demanded. So there are several examples. Okay, now after this preparatory work, we are now in the position to state the main result of this talk, which resides on an nth order effective optimal control problem. This effective problem has an effective energy or cost functional, J star m. I will come back to this in a moment, and an effective PDE constraint. Let's have a look. So this equation has constant coefficients a star to k, so only the even ones appear, and it's of order 2m in space. Now, although still depending on epsilon, this equation can nevertheless be regarded as an effective equation in the sense of homogenization, because the coefficients are, of course, constant. Finally, there is also an effective admissible set, U star at, which is simply defined as the inverse image of the original set under the Bloch adaption A epsilon, restricted to those functions theta with compact support k in Fourier space. Now back to the effective energy or cost functional. And again, it consists of three parts. So there's again this L2 norm of the control and an effective energy, E star m, which is exactly the natural energy corresponding to this effective PDE constraint. Now, what is really important to note is that the homogenization problem has also an impact on the reference data. Remember, the original data were assumed to be adaptions of certain functions UD1 and UD2, and in our effective model, exactly those functions UD1 and UD2 appear. So we are not taking the original data, but in fact the profile functions here. Okay, so this is our nth order effective model, for which we can prove that it's well posed. This will be discussed at the end of the talk. And we can also show that the following error estimate holds, namely, for the difference between theta epsilon star, which is the original optimal control, and the adaption of theta star m, which is the adaption of the effective optimal control, the L2 norm is actually of order epsilon to d2m. And the same holds also for the state functions. Now, this is the main result of this talk. So theta star m, the effective optimal control, is in some sense the profile function, which has to be adapted to the microstructure to yield a corrector of order epsilon to d2m. Now, before proceeding with the proof, let me maybe discuss a small example once again to demonstrate the definition of this effective admissible set. So once again, consider the set of all controls theta such that the L2 norm is bounded by this fixed constant L. And now remember that for functions with compact support in Fourier space, the Bloch adaption preserves the L2 norm, which means that the effective admissible set is exactly the same, merely restricted to functions with compact support in Fourier space. So even though this definition might look quite complicated at first sight, for specific examples, it can be very easy to obtain this effective set. Okay, now the rest of this talk is devoted to the proof of this result. And in fact, it consists of 3 steps. In the first step, we expand both the original optimal control theta epsilon star and corresponding state u epsilon star in Bloch waves. And we prove that, in fact, both functions are adaptions of certain profiles, theta epsilon star tilde and u epsilon star tilde. So this result simply tells us that there are profiles, these two, which, if you adapt them to the microstructure, give us exactly the optimal control and the optimal state. Then in the second step, we expand the lowest Bloch eigenvalue lambda 0 epsilon in a Taylor series. So this is somehow a classical step in Bloch analysis to obtain constant effective coefficients for our effective model. And then in the third and final step, the central estimate is stated, which tells us that the difference between theta star m, the effective optimal control, and this profile function theta epsilon star tilde is actually small in the L2, namely of order epsilon to d 2m. And that the same is true for the state functions. Now, actually, in order to prove this result, we will have to rewrite both problems, the original and the effective one, in Bloch and Fourier space respectively. And it will turn out as a major feature here that after leaving the physical space and translating everything into Bloch and Fourier space respectively, the admissible sets now are exactly the same, which makes the problems, of course, comparable by means of the corresponding variation inequalities. Okay, so let's start with step 1. So to this end, we expand both theta epsilon star and u epsilon star in Bloch waves. And we note that since u epsilon star is a solution to our highly oscillatory PDE constraint with right-hand side theta epsilon star, and since this operator here acts as a multiplier on the Bloch expansion, we can easily express the Bloch coefficient of u in terms of the Bloch coefficient of theta by simply dividing by 1 plus lambda epsilon m, which is the Bloch eigenvalue. Okay, in a second step, we then take a closer look at the cost functional, j epsilon, to derive that, in fact, the Bloch coefficients of the optimal control are only reduced to m equals 0, the lowest Bloch mode, and eta in k. So all other Bloch coefficients simply vanish, the one for m larger than or equal than 1, or eta outside k. Why? Well, this is because the cost functional, in fact, consists of 3 parts, which are L2-like. And so this L2-like terms can be rewritten in terms of the Bloch coefficients, producing also L2-like terms for the Bloch coefficients. Now, the Bloch coefficient of u can be expressed in terms of the Bloch coefficient of theta. So we end up with a cost functional in terms of the Bloch coefficient of theta only. And now, since the reference data were assumed to be adaptions, which means that they are also reduced or restricted to eta in k and m equals 0, it is not very difficult to conclude that this should also be the case for the optimal control. So in other words, Bloch coefficients others than m equals 0 or eta in k increase the cost functional. And since we assumed that the projection onto the lowest Bloch eigenvalue and eta in k is still admissible, so this is exactly where this assumption comes in, we can then conclude that the optimal control has in fact such a projected form. Okay, so in conclusion, we obtained a Bloch expansion of theta epsilon star and u epsilon star, which both turn out to be adaptions. Now in the next step, we expand the lowest Bloch eigenvalue lambda 0 epsilon in a Taylor series. Now remember the definition of lambda 0 epsilon. It was defined as 1 over epsilon squared times the original, not rescaled Bloch eigenvalue lambda 0, evaluated in epsilon times eta, which of course suggests to Taylor expand lambda 0 around 0. And this is in fact possible. So it turns out that lambda 0 depends analytically on eta in the neighborhood of 0. This is a non-trivial but very fundamental fact in Bloch theory, so it's well known. And it's also well known that lambda 0 of 0 vanishes, and that it's also the case for all odd order derivatives. And so we finally end up with the following Taylor expansion of lambda 0 epsilon, where, as you can see, only the even orders appear. And now by truncating this series at order 2m minus 2, we are left with an approximation error of order epsilon to the 2m, which, and this is now the important point, which is uniform in eta, because eta is restricted to a compact set. Okay, and now with this knowledge, it's not very difficult to obtain a first approximation by simply replacing lambda 0 epsilon in this formula by this polynomial Pm. And it can easily be shown that these functions are close in L2 because the formulas just differ by the blue terms, which are shown to be close uniformly in eta. Now, what is really interesting about this first approximation here is that it's in fact related to theta epsilon star tilde through our effective PDE constraint. So it's a solution to our effective PDE constraint, but with right-hand side theta epsilon star tilde. And this is at the same time annoying because what we would like to have is a right-hand side theta star m, which is the effective optimal control. So this first approximation solves the effective PDE constraint, but with the wrong right-hand side, namely theta epsilon star tilde instead of theta star m. And so in the next step, we will prove that in fact, theta star m and this theta epsilon star tilde are close, which is done by rewriting both problems in Bloch in Fourier space. Okay, so to this end, we rewrite our original optimal control problem in Bloch space and our effective one in Fourier space to obtain two cost functionals, which actually only depend on the Bloch and Fourier coefficients of the control. And note that the highly oscillatory PDE constraint is already incorporated here, because this is exactly the Bloch coefficient of the solution to this PDE constraint with right-hand side theta epsilon. And here everything is restricted to the lowest Bloch mod m equals 0, because we already know that the optimal control has such a reduced form, so we can restrict our minimization problem to only those functions with contributions in the lowest Bloch mode m equals 0. Likewise, the effective PDE constraint is also incorporated here, because this is exactly the Fourier coefficient of the solution to our effective PDE constraint with right-hand side theta. So to sum up, we obtained two cost functionals in Bloch in Fourier space. And now the question is, what are the admissible sets? I mean, in the original setting, we have the admissible set U epsilon ad, we have this effective admissible set U star ad, but can we translate those sets into Bloch and Fourier space respectively? And it turns out that we can, and it even turns out that the translated sets are actually the same. So remember the definition of our effective set U star ad. It was defined as the inverse image of the original set under the Bloch adaption, and then restricted to functions with compact support in Fourier space. So in other words, a function theta f with Fourier coefficient theta hat is in this effective set if and only if a function theta b, which is actually the adaption of theta f, lies in the original set. And so I can easily derive this equivalence here, which at the end shows us by construction of the sets that both minimization problems in Bloch and Fourier space respectively are in fact constrained by the same admissible set, which we denote by U hat ad. And this is a major feature because this makes it possible to compare both problems by means of the corresponding variational inequalities. And this is what we do next. So we easily find out that for the minimizer of the original problem and the minimizer of the effective one, the difference is actually small in the two, namely of order epsilon to d2m, because the corresponding cost functionals basically only differ by the term lambda 0 epsilon, which in the effective problem was replaced by the polynomial Pm, and we know that the difference is small uniformly in eta. Oh, I'm sorry. So it's not very difficult to prove this inequality. Now, this inequality is an inequality in Fourier space. So we have to lift it into the physical space by applying parseval identity, which tells us that the L2 norm between the corresponding functions, which is theta star m, the effective optimal control, and this theta epsilon star tilde, is actually also small. Okay, now this first estimate is an estimate on the level of non-oscillatory profile functions. As we already know, the original optimal control is in fact the adaption of this theta epsilon star tilde. And so to obtain a corrector for the original optimal control, we need to apply the Bloch adaption, which for functions with compact support in Fourier space preserves the L2 norm. And so the result is exactly the same. It's of the same order in epsilon. Okay, and this concludes the corrector result for the optimal control. Now, what is still missing at this point is, of course, an estimate for the corresponding state functions. And therefore, remember that we already introduced the first approximation of the state function by simply replacing lambda 0 by this polynomial Pm. And the difference was small. Now, unfortunately, this first approximation solved the effective PDE constraint, but with the wrong right-hand side, theta epsilon star tilde, instead of theta star m. But now, since we already shown on the previous slide that theta star m and theta star epsilon tilde are close, by applying a priori estimates for effective PDE constraint, which are available, we can conclude that this is also the case for the corresponding state functions. And again, this is an estimate on the level of profile functions, so we need to apply the Bloch adaption to obtain a corrector result for the original optimal state u epsilon star. Okay, and this actually concludes the proof. So in the remaining few minutes, I would quickly like to discuss the well-posedness of our effective problem, in particular focusing on the effective PDE constraint, which is this one here. So once again, this function has constant coefficients a star and is of order 2m in space. Now, of course, the first coefficient in this equation is the standard homogenized matrix, which is positive definite. However, already for the second coefficient, a4 star, it is well known that it has the wrong sign. It's negative semi-definite, as has been shown by Nkonka, Orif, and Vanina Tan in 2006. So in particular, our equation is not well posed in general. Now, this can be made obvious by just trying to write down the equation in Fourier space, and then you see that you really get into trouble for eta large, or large values of eta. However, in our case, the right-hand side theta is restricted to functions with compact support k in Fourier space. And this really saves us because in this case, the first quadratic term in Pm, it has the right sign, it's positive, and it dominates the other terms. In other words, one can find a threshold, epsilon m, such that for epsilon below this threshold, our equation is indeed elliptic with corresponding a priori estimates. Now, of course, this threshold epsilon m depends on the order of approximation m, and even more important, it also depends on the size of this compact set K. And in particular, the results presented here are only valid for epsilon below this threshold epsilon m. Now, of course, such a threshold is also a drawback because in practice, one usually likes to have an effective model which is well posed independently of epsilon. And this, in fact, can also be done. This approach is based on a substitution trick, which I would like to sketch in a fourth order equation only. Later on, one can generalize things to arbitrary order. But let us consider only the fourth order equation here with a2 star and a4 star. So this equation is already not well posed. And now the idea in 1D, so in 1D, the idea is very simple, and in the context of wave equations, it's also known as the Well-posedness trick. So in 1D, the idea is to rewrite the bad term, the one with the wrong sign, in this form, and then to replace A2 star times the second derivative of u to lowest order in epsilon. So what is the lowest order approximation? It's u minus theta. This already has higher order. So to replace it to lowest order in epsilon by u minus theta. Of course, this is only formal at first sight, but it can be made rigorous. And if you do so, a miracle happens, because now the resulting equation turns out to be well posed, because this A4 star divided by A2 star, it's negative, it has the right sign. And in fact, this can also be generalized to higher order dimension. The calculation is a bit more complicated, because we cannot rewrite the bad term in exactly the same form as in 1D. Instead, we have to allow for a remainder with a right sign. So in fact, one needs to derive a decomposition, but it is possible, can be shown. And if you now do the same thing, you replace A2 star times the second derivative of u by u minus theta, you end up with a well-posed equation. Okay, and this in fact is a well-posed model independently of epsilon, and one can indeed prove that its approximation order is exactly the same as the model I showed you before. And this can be done for arbitrary order, so order m equations too, which removes the problem with the threshold. Okay, and with this, I would like to thank you for your attention, and yeah, I'm looking forward to your questions.
Thank you so much, Agnes, for your very nice talk. I think there is a question in the chat box. Can you?
Yes, one moment. I have to read it. The integral transforms have smoothing properties. One moment. I'm not sure that I understood the question correctly. So this integral transform has smoothing properties. Well, they are not smoothing in fact. I mean, the assumption of compact support in Fourier space is already a very strong assumption, saying that the function is in fact very, very smooth. So you don't have to smooth it in some sense. Maybe I don't understand the question correctly. Could you please maybe say what exactly is meant by this?
Can we unmute Julia?
Yeah, for theta, we need strong convergence. Yes, of course, that's right. I mean, we do have strong convergence, and the standard homogenization results, they get it right with standard weak convergence methods such that it works, in fact. So this is fine. Yeah, for the fluxes of U, you can get convergence strongly in L2 and weakly in H1. So grad U converges weakly in L2. This is also fine. So the gradient of the state function. And of course, the fluxes themselves do not converge strongly, which is why you have to correct them. Yes, the admissible theta does not converge strongly. That's true. So only the correction can be better in the convergence. Okay, I'm not sure that I really understood it correctly. Maybe I could answer to the other question first. So you are absolutely right that compact support in Fourier space is something which is extremely strong, and you cannot really demand it in practice. So UD1 and UD2 are compactly supported in Fourier space. Let me just say that it would be sufficient to just assume some kind of decay of the Fourier transform. So this compact support is in fact not not really necessary. You could work, for instance, with Schwarz spaces, and then this would be also sufficient to derive estimates. The compact support is very nice to treat, but in fact, you could replace it also by a decay. What will happen when UD1 and UD2 are also compactly supported? Well, the Bloch and Fourier method is a spectral method, and it really needs the compact support or the decay in Bloch and Fourier space. And you cannot conclude this from a compactly supported function. So in physical space, a compact support doesn't have the nice properties which you need for the Bloch and Fourier space. So this wouldn't give us the right thing. I hope this answers the question. I'm not sure.
Okay, very nice results. Excellent and interesting talk, Agnes. Thanks a lot.
Thanks.
Okay, so I think,
yeah,
yes, please unshare. So thank you so much. Very clear presentation. Okay, so thank you again, Aredel and Agnes.